Bismillahirrahmanirrahim. Today we'll be talking about work done by quasi-static pressure. Quasi-static work done by pressure. This lecture is a part of lecture series from the course of statistical mechanics. The course code of this course is PHY231. In today's lecture, we will basically try to understand the work done by pressures, and we also need to know the quasi-static process. The work done by the pressure is also a topic of today's lecture. We also need to know the exact and inexact differentials at the end of these lectures. So for this purpose we are considering a simple systems, that is a system of interest is the gas that is enclosed in a cylinder, and we can move the systems, we can move the piston up and down to do work by the systems. There are two ways: one is work done by the system and other is work done on the system. So we can consider all the cases separately. But before considering the systems in detail, we need to know that the system is isolated from the surrounding. If you look at this figure, here is a great insulation which is making isolation of the system from the surrounding. So the system is not exchanging energy with the surrounding, except there is a thermal reservoir, and that is actually called as a heat source, and from this it can get heat when it is required, and we can control the magnitude of that heat. And similarly we have a piston. This is a piston, and we can even increase or decrease the weight of this piston by reducing or increasing the magnitude of mass that is present on this piston. So as a result, the piston can move up and down depending on the different configurations. And similarly we can control the magnitude of energy in that system, or thermal energy of that system, by the heat reservoir that is actually called as the thermal reservoir. So we need to understand the quasi-static work done by pressure on the gas. So for this purpose we need to consider the situation that is presented here. In this, a gas is confined to a container. The volume of this container is V. Having the piston of this container is at the top of this cylinder, and there is a weight on the top of the piston which is changed by adding small lead rods to it. We can increase or decrease the magnitude of weight of the piston by increasing or decreasing the lead in it. So initially the piston and the gas are in equilibrium. So if the weight is increased, so what happens? The equilibrium situation is disturbed because the weight of the piston increases. So the piston will push down on the gas, because due to the increased weight, the piston will push down on the gas, and what will happen? The pressure will increases because the work will be done, and work is done on the gas. So if the weight is decreased, so what happen? The gas will move up, the piston will move up, the gas will be relaxed, and the pressure will reduces. So what will happen? The work on the piston, the work will be done on the piston. So we have these two extreme cases where work is done on the gas and work is done on the piston. In both cases, in one case we increase the weight, the piston move downward in this direction, and the other case it can move upward if it reduces the weight. So it means the piston can move up and down just by increasing or decreasing the lead rods. Similarly, the pressure inside the gas can also increase or decrease with the help of thermal reservoir. If we increase the magnitude of heat in that systems, so as a result, if the weight is constant, the pressure will increase and the piston will move up if it is flexible. And if we extract some heat from the system, so what will happen? when the heat is extracted, the pressure will reduces, and definitely as the weight is constant, so the piston will move down. So for elementary physics, what we need to know, we need to calculate the differential work done, the small amount of work done by the gas when the piston undergo a vertical displacement. In both cases, whether it move up or down, but that is the type of vertical displacement by the piston. So the magnitude of work done could be calculated as a dW, that is actually the differential work done. d-w is actually the differential work done, and the magnitude of this differential work done, dW, is equal to FTS. Here F is the total vertical force on the pistons, F is the total vertical force on the piston, and how we can calculate the force, that is actually the pressure. Pressure is actually force per unit area, so that is F is equal to PA. A is actually the cross-sectional area of the piston, and volume, how we can calculate the gas volume, we can get the gas volume by VAS. A is the area and S is the height of the pistons. So from that we can get the volume of this piston. So we can put the value of AS in the equation, above equations of what happened. We can put both the value of F and AS and this equation, so it will be PADS, or ADS is equal to dV, so it will be like PdV. So this is the magnitude of work done, differential work done by the system, and that is equal to dW is equal to PdV. So the work done by the gas and the volume, the work done by the gas as the volume changes from the initial volume to the final volume is given by the integral of the pressure P as a function of V. So we can calculate the magnitude of work done over here. This is the total work done, and that is actually, we take the integration of the work done, putting the value of dW over here. We can integrate and the system between the initial pressure and initial volume and the final volume, and obviously we can get the magnitude of work done. So this integration actually shows the area under the curve, area under the pressure PV curve, or that is the pressure volume curve. So how we can get the value under the curve? It depends upon different situation. Let's consider example. This on vertical axis we have a pressure, and horizontal axis we have volume, and we have the system is moved from one configuration from initial state to final state. So what happened in this case? Work is greater than 0. So I mean the system moves in this way that it is moved from the initial position I to the final position O, and this is the simple process which could be elaborated. The same process we can represent in a different way if we can move the system through this path. In this case also the work is greater than 0. The system is moved from initial position I to final position F, and that is actually it is moving from I to F through this path. In this case the work is also greater than 0, and the W is greater than 0. So there are many possible ways in which we can consider. So we can consider the inexact differential for this particular case when we describe that, and this actually describe the many possible processes that are involved in this particular systems. So we are considering another some closed path and some simple path, in which we have 4 possible processes, and in this 4 possible processes, let's consider the first process, that is the bringing the system from initial to final position through this path. In this case area under the curve is over here, and the work done is greater than 0. This is the area, the yellow color shows the area under the curve, and the work done W is greater than 0. Now we are coming toward the other configuration where we can bring the system from initial to final position. In this case work is less than 0, but we are treating the work is done at the cost of the internal energy of the system. But you look at the direction of the system. In this case the system was coming from high pressure towards the low pressure. So as a result, work could be greater than 0. But in this case, this is the direction of the work done, of the system movement. But in this case, you see, this is the opposite direction, so that is why work should be less than 0. The system is taken from the final state to the initial state. Initially, at this point, the pressure is low, and at this point, the pressure is higher. So how we can increase the pressure, the magnitude of pressure? So we can do it with the help of increasing force. And in this case, work is done at the cost of internal energy. In this case, work is done at the cost of internal energy, but in this case, the pressure is increased. But how it can increase? We can put the force or the weight on the piston, and as a result, the pressure increases. Let's come toward this case. We are moving the system from I to F, from initial to final position. One is this path, G, H, F. The system is moved through this path here, 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 and other is this path. We can move the system from from C, D, F. This is another path for this particular system. Here we have a system that is brought in a closed path, where net work is greater than 0. So this is area under the curve that is present inside the curve or inside the closed path. So this particular systems. So we need to discuss something about exact and inexact differential in the upcoming slides regarding the calculation of the work done. So if we have infinitesimal quasi-static, we have a type of a process in which the changes are infinitesimal. So and the process is quasi-static. So the first law of thermodynamics we can modify accordingly. So actually is it equal to Q E plus W. So it will be like, because the process and then the changes are infinitesimal or very, very small. So the changes could be represented as a dq is equal to dE plus dW. Here d is an exact differentials, and both dq and dW are inexact differential. So that is why it's very important for us to understand the exact and inexact differentials. So we need to come briefly to understand the exact and inexact differentials. So let's come toward the exact differentials. What is the concept of exact differentials? For this purpose, we need to consider f of xy, that is an arbitrary function of x and y, and fxy is a well-behaved function satisfying all the match criteria for being an analytic function of x and y. So its exact differential could be written as d of f of x of y should be equal to a into x of y dx plus b into x of y dy. Here we can see that a of x of y is equal to curly by curly x f into y, and similarly b of x of y should be curly divided by curly f by curly y f. So this is the type of x. So if f of x is an analytic function, then its second cross its partial derivative must be equal. So we can get the partial derivative of this cross. So that is like curly square f divided by curly x curly y should be equal to curly square f divided by curly y curly x. So here f of x of y is an analytic function. The integral of df between the two arbitrary point, that is 1 and 2, and that is described in the previous example, where we have this, we are bringing the system from initial to final position. So that is the calculation for that, and for that we have f of x, that is the independent of path between 1 and 2. So we are coming toward the arbitrary analytic function, that at f of x. So the integral of dff around an arbitrary closed path vanishes, that is equal to 0, and we can take the integral, and the closed path, the integral around the closed path should be equal to 0. So we can have some more discussion on exact differential, and that is actually there are 3 tasks for that. So this is the best way of finding of d of f of x of y of an exact differential is to see if there is a change in that variable. There are curly by curly y a into x when x is constant, and similarly curly by curly x of p when y is a constant. So these two should be equal to each other only if and only if f of x is a function of both x and y. So similarly we can have another condition for that, and in this condition f depends upon both variable, that is x and y. So df should be equal to f of x2 y2 minus f of x1 y1, and that is actually equal to, because that is two position and we are dealing with the two-dimensional space. The two variable that is available in this system is x and y. This variable, that is x and y, and that is actually volume and pressure in this particular case, but anyhow it's a two-dimensional, so this should be x and this should be y, and in this case is volume and pressure. So we can have the change, and that is actually f of x2 y2 minus f of x1 y1, that should be equal to f2 minus f1, or we can take the differential between 1 and 2 of df. So thus integral of definite integral of 1 over 2 a dx plus b dy does not depend on path, so it's independent of path. That is another condition. And the third condition is to find f from df, that is we can use we need to integrate it. It's very easy, just integrate df. It should be a dx plus a constant quantity, that is f of y, and that should be equal to b dy plus gx. That is another condition for that. So we can consider a simple process for a gas, that is the quasi-static work done by pressure, and that is done when the gas expands. Here, just like in the first slide, we consider this particular gas, so in which case the work will be done by pressure. When we reduces the weight, so as a result work will be done by pressure. The piston will move up and work will done by the pressure. So this is actually the very small change, so that is why we are considering infinitesimal change, that is that is here. So in this case work is done by the pressure, as actually we already discussed in the beginning of this slide, that there are both the possibilities are there. If you are increasing the weight, work will be done on the system. If you are reducing the weight, work will be done by the system. Increasing the weight will move the system in downward direction, here in this direction, in downward direction, and because the weight will increase, it will move down and the pressure will be increased inside the system. And reducing the weight, what will happen, the system will move in the upward direction, and what will happen, the work will done by the pressure or by the systems, and as a result the energy of the system will be reduces, the pressure will be reduces, and the piston will move up. But in other case, when the work is done on the system, the pressure inside the system will be reduces. We are not considering the thermal interaction in this particular case, and we are considering that the systems are not interacting with the surrounding by thermal means. It is insulated completely from the surrounding, so that is why we just skip this portion. But anyhow, we are considering about the quasi-static work done by pressure. So let's come toward the work done, that is presented here along different paths, and its magnitude of path, and we need to define that the work done does not depends upon the path. So that is for a particular gas, the quasi-static work done by pressure. We are bringing the system from this initial configuration to this final configuration, or maybe we can move through the closed path, and we have two possibilities for that. One is path 1, another is path 2. This is a type of PV diagram. This is the volume axis, this is the pressure axis, and this is the initial volume, this is the final volume of the system. At this case the volume has been reduces, and in this case volume is high. Similarly, at this particular case the pressure increases, and here we have low pressures. So in this way, when we calculate the integral, we can get the information from this integral that this is the path dependent is clearly GTW is a path dependent system. But if we can get the del E, the total amount of energy, that is actually the path independent. Does not depends upon time, and this is something about the work done by pressure in today lectures. Hope to have new lectures in the next class.